Across the country, Amazon employees are turning hourly jobs into higher-paying careers.
I heard about this design apprenticeship program with Amazon, and now I'm a UX designer for Prime Video.
Learn more at aboutamazon.com.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again. Great to have your company here on Space Nuts, the podcast. My name's Andrew Dunkley, and Fred Watson joins me, as always, from the Australian Astronomical Observatory, or from his lounge room, depending on where he is at any given time. Hello, Fred.
Good day, Andrew. How are you going?
I'm well, and you?
Yes, I'm still in the lounge room.
Well, it's very comfortable and very cosy, and why would you want to be anywhere else?
Of course, that's right.
Now, today, we're going to look at a few things, including a listener question, which is always welcome. But we're going to talk about solar flares and why they happen. They think they've unravelled the mystery of solar flares. So we'll talk about that. And we've talked about this in the past, but I'm glad it's come up again. NASA finally looks like it is going to send a submarine into space and plonk it down on a moon, I suspect. And that's very exciting news. Which one and why? I guess we'll learn. And colliding dark matter, a question from Andrew Mitchell. We'll get to that for you soon, Andrew. But first, the mystery of solar flares and why they happen. Have they figured it out, Fred?
Apparently they have, and in a lot of detail, and with terminology that I think it makes it easy to understand. Well, I think it does. So
maybe for Mandu the cat, but not for
well, quite right.
Not for
yes.
me.
Look, he's across all of this, I can tell you. He sleeps through most of it, which is probably the correct answer. So we know that the activity of the sun, of course, dictates some of the things that happen here on Earth. So if you've got things like solar flares, they unleash beams of charged particles into the sun's outer atmosphere, which 3 days later or so often get to the distance of the Earth and actually can interact with the Earth's magnetic field. And so we get displays of aurora borealis and aurora australis, and also sometimes disruptions to power supplies and communications. So we need to know about these things. We need to understand what solar flares are all about, how they work, how they are caused. And because of that, NASA in particular has, but other space agencies as well, have a flotilla of spacecraft in orbit around the sun, actually studying the sun's surface. And principally because of those, but also because of ground-based observations too, we now know that the role of magnetism in these phenomena is very, very high. So the whole thing is basically driven by magnetism. And there's a lovely statement, actually, it's on the BBC report on this, which summarizes it so well. Generally speaking, solar eruptions are caused by a sudden, violent rearrangement of the sun's magnetic field. And that's what it is. Often it is a kind of magnetic twang. The field lines are broken, and that releases the plasma from the sun's inner atmosphere out into space, where it belts off across the solar system and can interact with the Earth. But there is now a lot more known about the kinds of structures within the sun's atmosphere that cause these processes. They're often associated, Andrew, with sunspots, which we see, even in small telescopes. You should never look at the sun through a telescope, but you can, if you've got a solar filter on, especially made piece of equipment, or you can also sometimes project the image of the sun through the telescope onto a sheet of paper or cardboard, so you're always looking with your back towards the sun. It's easy to see these dark spots on the sun when you do that, the little black dots, which actually have been known since before the invention of the telescope. William Herschel thought there were holes in the outer atmosphere of the sun that let us see down to its cooler surface underneath, and he expected to see people wandering around on there. But yeah, he never quite found those. But what we know they are now is regions where the temperature is slightly lower. But more especially, we know that they are regions where these complex magnetic processes are taking place. So there are two kinds of structures, and these are the ones that are now being more deeply understood. One is called a magnetic cage. And a magnetic cage, if you imagine the magnetic field lines, which are the sort of thing that at school we used to demonstrate with a bar magnet and iron filings.
Oh, yes, I love doing that one.
That's right. They're lined up along the field lines. So in a way, that's a crude model of a magnetic cage. It's the field lines which are between two poles of a magnet, and the magnet, of course, is on the sun's surface. It's where the sunspot is. So this magnetic cage also contains something else, though, a different set of magnetic activity, and these are called ropes, magnetic ropes. So the magnetic ropes sit within the magnetic cage, and the rope itself is almost like a twisted skipping rope. It's actually in very vigorous motion. This is not a real rope, it's just a rope of magnetism, if I can put it that way.
Yeah.
So if the contortions of the magnetic rope are strong enough, they will break through the magnetic cage that confines them, and that produces a plasma eruption, something we call a coronal mass ejection. Mm-hmm. It's like a very strong solar flare, and so the cage itself apparently plays a very important role in all this. It's how strong the cage is depends on how well confined this energy is that the sun wants to spit out. But if you've got a strong magnetic cage, it won't do. So what's happening in this research is a combination of observations made by these various NASA spacecraft, these various spacecraft, such as NASA's Solar Dynamics Observatory. That's one that's actually looking at the sun constantly, but also using supercomputers to run simulations of what these things would do. It is really interesting stuff. I have to say that I'm not an expert on the sun's the dynamics of the sun's magnetic field, although I'm very interested in its effects, particularly when it causes aurorae near the north and south poles of the Earth. There was one particular solar flare that these researchers studied. Many of them are actually from a French institution. This was one that took place in October 2014, and using the Solar Dynamics Observatory data, combining it with their supercomputer simulations, they determined that with this one, there was not enough energy within the magnetic rope to actually smash through the magnetic cage and cause a coronal mass ejection. But despite this, the rope became very, very highly twisted, and what it produced was a large level of magnetic instability. And apparently that sort of upset part of the magnetic cage, and that allowed the solar flare, the blast of radiation, to actually come through. And in fact, that did have some disruptions on the Earth when it reached the Earth. So what is the point of all this? Well, the point is to try and use these these solar observatories, the spacecraft themselves, to be able to predict exactly when a flare is going to occur and what its intensity might be. At the moment, all we can do is observe them and report them. We see a flare happening on the sun. We know if it's pointing in the right direction that a few days later we're going to get activity on the Earth. That's the job of these observatory spacecraft, the Solar Dynamics Observatory and others. But if you can combine, observations of these magnetic fields with with the supercomputer simulations, then you might be able to say, well, in a day or two, we expect there's going to be a solar flare here. And that then gives you longer warning as to what its consequences might be on the Earth.
And that's the big concern, because if we suffer a direct hit by a solar flare, we might have another effect like they had in 1859 with what I think they called the Carrington event, which wiped out telegraph stations because of the intensity. Now, they didn't have the technology then that we've got now, so imagine the effect today.
The Carrington, that's right. The Carrington event is the strongest solar flare in recorded history. And indeed, it was in the infancy of electric telegraph, particularly in the United States, where the railway era was in place. And it fried them all. It basically fried all the equipment. You're absolutely right that we are now so dependent on electronics, particularly in space. We have flotillas of satellites that do all our day-to-day business for us in terms of communications and surveillance and resources management. All of that stuff is the province of spacecraft. If you fry all those, then you're in big trouble. It is true, though, that we now know of the risks, and so the really sensitive bits of spacecraft are protected within reasonably hardened metallic shields. But still, it is a risk that we on Earth take in our modern era, and that's why funds are being invested in checking out what's going on the sun and trying to understand it.
Well, it sounds like we're one step closer to that with the discovery of how these ejections take place. So that's good news. So maybe we're in a position where we'll be able to go, okay, unplug your computers, bury them about 50 feet under the ground, and fingers crossed.
That's right.
You're listening to Space Nuts. Andrew Dunkley here with Dr. Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons, and there was just something about their business model that I particularly liked, and a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show. Now, Fred, to one of my favourite topics. I've brought this one up with you a few times, and I'm really excited to hear that there is now confirmation that NASA is planning to send a submarine into space. I hope it's yellow. I don't really care what colour it is, but this is really exciting news.
It is. It's still a project in its infancy. it's a group of NASA scientists, and there are also university scientists involved with this, who would like to propose sending a submarine to Saturn's moon Titan, which we were talking about only a few weeks ago.
That's right, yeah.
Titan, an extraordinary world, the largest moon of Saturn, explored pretty well by NASA's Cassini spacecraft. It's the only place in the universe other than Earth where we know there are liquids on the surface. And that makes it a very, very special environment. The liquids are not water. The temperature on the surface of Titan is minus 184 degrees Celsius. That is the liquid temperature. It's actually a liquid natural gas. It's a mixture of methane and ethane, very toxic, of course, if we were around, but might just be a place where what you might call hydrocarbon microbes might have developed. There is quite a body of opinion that suggests that maybe living organisms, fairly rudimentary organisms, but living organisms with which use, rather than water as their working fluid, as all life on Earth does, that use ethane and methane as their working fluid, maybe these things are swimming around in the seas of Titan. So what we want to do is explore them. And that is the topic of, I think, a number of what you might call blue sky proposals that are being put to NASA. NASA has a very rigorous process of determining which spacecraft will go ahead and what projects and missions will go ahead. I don't think any of these have yet got quite near the really sharp end of the process, but certainly scientists are already working on this sort of project. So just to give you an idea of the geography, these lakes and seas are near the northern polar region of Titan. They are in what you might call depressions, I suppose, not in the rock, because Titan doesn't have a rocky surface. Its surface is made of solid water ice at minus 184 degrees Celsius. It might as well be rock, but it's very, very solid. And so the lakes and seas have pooled in depressions in those in the troughs of the northern region of Titan.
Do we know why they're only in the northern hemisphere?
It's thought to be due to the sort of almost like the tectonic activity on Titan, the influence of the fact that Titan is a moon going around a big planet which has tidal forces imposed on it by the planet. I have read papers about why they're in the northern hemisphere, and also why they only seem to fall within one specific area of the northern hemisphere, which is kind of more or less rectangular. It's very interesting. I think it is to do with the gravitational influence of Saturn. Because remember, I believe I'm right in saying that Titan is tidally locked to Saturn, so it always keeps the same face towards Saturn. Anyway, the lakes and seas are big. The biggest one, Kraken Mare, has something like 400,000 square kilometers of liquid. It's actually in two parts. It's they're separated by a narrow channel. The second one is Ligeia Mare. That's not quite as big, but they're comparable in size with the Great Lakes of America. So they're not small bodies of liquid. And you can imagine that a submarine would really be a great way to explore them and find out what's going on the sea beds, if I can put it that way. Do we know how deep these mare are? Yeah. I think the deepest point of Kraken Mare is about 300 meters. Ooh. It's sizable stuff. And they're real, they are real seas, these things. They're not being called seas just in a gratuitous way. They're very large. So what's been happening? Well, Washington State University in the United States has built a test chamber. That's why this is in the news at the moment. They've built a test chamber that houses the same mixture of that we believe these seas on Titan are made of, ethane and methane, at the same temperature, minus 184 degrees Celsius. And they've built that chamber to explore some of the properties of this supercooled liquid, because I know that researchers have looked already. I remember reading something a year or so ago about the concerns that any submarine or other underwater vehicle would stir up bubbles in the liquid because of the heat that it produces. It produces heat as it's driving along, and that actually causes bubbles, which actually make it almost impossible to steer the submarine around because the thing's surrounded by bubbles. So they've basically, the people at Washington State are doing that simulated test chamber to try and understand what happens when you put a submarine in these sorts of temperatures and you release heat into it. It's really, a kind of blue sky science, because we know about liquid natural gas, but we don't really know how it behaves in an environment like this one where the ambient temperature is so low. It is possible that the temperatures might get low enough on Titan that would freeze these lakes, and that's really interesting because there is some nitrogen in the liquid as well. It's not just ethane and methane, and that modifies the temperature at which it freezes. We know that Cassini observed things that might be icebergs in the large lakes and seas of Titan, and icebergs themselves, these were things that seem to come and go, and there was a suggestion that as the temperature changes they sink to the bottom or rise to the surface. Studies like that are really important before we actually start planning missions to these places, because the last thing you want to do is send a submarine to Titan and then have it run into an iceberg. It would not be a good look.
Oh, that's never happened before.
No, it's never happened.
So, yeah, I guess I got a bit premature when I thought they were actually doing this, but there's a lot of things they've got to consider. I suppose the other thing is, would a sea made up of these kinds of petrochemicals, if you like, be corrosive? And, they'd have to allow for that. So no rubber parts.
Yes, that's probably true. I mean, rubber's going to be pretty inflexible at those temperatures anyway. But yes, the corrosion question is a good one because it's something that is fairly foreign to us. Now, the fact that we keep liquid natural gas in steel containers here on Earth probably suggests that you can be reasonably sure that it's not going to corrode things. But there will be certain materials that you would not want to use on these.
Another factor is, I know I've been out very early to play golf in -2 or -3 degrees, and my mobile phone shuts down because the battery can't handle it. So at these temperatures, that's another issue. I assume these things are going to run on battery.
They would have to. That's correct. Yeah.
So that's another thing they need to figure out.
A lot of work ahead. I hope we see these things going to Titan within our lifetimes.
I do too. I really want to see them plonk one down there and see what we can find. And you and I have spoken many times about the search for microbial life within our solar system. Here's an opportunity. I reckon take the bull by the horns and see what happens.
Absolutely.
Get there.
I'm with you there.
All right, we'll keep an eye on that particular story, of course. You're listening to Space Nuts with Fred Watson, and I'm Andrew Dunkley.
3, 2, 1.
Space Nuts.
Finally, Fred, another audience question. We love these. And again, like last week, this one's got some supercomputer thinking going on here, I reckon. Hi there, Andrew. I've just listened to the latest podcast, which is not the latest podcast anymore. Fascinating story on Australia's own satellite and rocket launch. Gee, this one does go back. Sorry, Andrew, we've been really slow in the uptake with this one. I have a question for Fred. Your discussion about the possible first detection of dark matter got me thinking about whether dark matter would interact with itself gravitationally. If so, there may be potential that it would clump together and collide with itself. So could a future gravitational wave observatory detect collisions between dark matter bodies? That's a good one. And look, he's asking a what if question, I think, but worth investigating.
Yes, it is. And it's a good thought. I mean, we know that gravitational waves are caused by masses being accelerated. So I think the kind of scenario that Andrew describes is not what would produce gravitational waves, because what you would have will be a cloud of dark matter, and it's whatever subatomic particles they are. This is as yet an unknown species of subatomic particle. And if the dark matter particles were interacting gravitationally, it would not be a sudden acceleration of a single mass, which is what you need to actually stir up space-time enough to produce gravitational waves. But it is a great question because we believe that dark matter particles do interact with each other, that they do collide, and there is a theory that if dark matter particles are a particular hypothesized species of subatomic particle, and I think these are probably axions. There's things called neutralinos which are a candidate for dark matter particles, as are axions. I think this refers to axions. If they collide, then what they will do is annihilate each other, but produce gamma rays. And gamma rays are like high energy light waves, but they have a particular spectral signature. That's to say, if you analyze the different wavelengths of gamma rays that are coming out, then you'll get a peak at certain wavelengths, which is a signature just of these dark matter particles being annihilated. So that's one of the areas that people are studying. They're looking in the centers of galaxies, which is where we think the density of dark matter particles is highest. We think they clump together in the middles of galaxies. So they're looking there for any sign of this gamma ray signature that might betray large numbers of these particles colliding and annihilating. To the best of my knowledge, that has not yet been seen, although I think there have been some tantalizing observations actually made in our own galaxy. We are 25 or so thousand light years from the center of our galaxy, so it's the obvious place to look for these self-annihilating dark matter particles. And I believe tantalizing signals have been seen, but nothing yet that determines that, yes, we have at last identified what dark matter is. It's good thinking, though. It's probably the way that we might find out exactly what's going on.
Yeah, maybe. And it's a difficult question to answer because everything about dark matter is virtually theoretical. It's a matter of combining ideas and see which ones are workable, investigating them further, try to find the proof. But so far, not much. Not much going on there. We just know it exists because there's just so much that's not detectable in the universe, but we know something's got to be there.
Yeah, it's detected really by its gravitational influence on things that we can see. So, it's the classic observation that galaxies should be flying apart if there was no dark matter there, but the gravity of the dark matter is what holds them together. Yeah. So the evidence is very, very strong for the existence of dark matter. It's just finding out what it is that's the tricky bit.
It's all this dark stuff that we can't see. Like we know black holes exist, but we just haven't actually observed one directly. And this is another example of it. We know this stuff probably exists, but we just don't see it.
Yes.
We could just turn the light on and there they are. I mean,
it would be nice, wouldn't it? Maybe in some way there'll be a kind of a metaphorical light that we can shine on dark matter particles and work out what they are.
Maybe. All right, Andrew, thank you so much for the question. Hope we made a dent in answering it for you, and keep the questions coming because we do enjoy trying to solve some of the puzzles you come up with. Well, I don't. I wouldn't have a clue, but Fred does. It's a big kick out.
I wouldn't have a clue either.
Fred, thank you so much.
Great pleasure, Andrew. Good to talk to you, as always, and we'll speak again soon.
We will indeed. That's Fred Watson from the Australian Astronomical Observatory. Keep the cards and letters coming in if you're old school, or maybe message us via Facebook and Twitter. We do enjoy that too, and we would love to hear from you as things develop. And if there's a topic we've discussed that throws up questions in your mind, and that is the nature of astronomy, then fire off the questions, because it might just open up a whole new dialogue that could solve one of the great mysteries of the universe. Who knows? But we'd be pretty keen to hear from you. So thank you again for listening. Don't forget to share us on Facebook and Twitter and tell your friends and write nice articles about us in the press. And we will talk to you next time on Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.